Now, while Kepler worked with math, Galileo turned a telescope to the heavens. He didn't invent it, but he was the first to use it to study space. So, can you imagine being the first human to see craters on the moon or moons around the Jupiter? So, Galileo quickly built his own telescopes after hearing about them. He rushed his discoveries into a book, The Starry Messenger. So, this was the first scientific publication that shared telescopic observations of the sky. Imagine how shocking it must have been for readers in 1610 to suddenly learn the moon was bumpy, Jupiter had moons, and the heavens were not perfect. So, here are some of his discoveries. So, the moon was not smooth and perfect like Aristotle taught. It had mountains and valleys. And through the telescope, the Milky Way broke into countless faint stars. Even more shocking, Galileo saw 4 small stars orbiting Jupiter. So, on the left, you see Galileo's original sketches of Jupiter with 3 to 4 dots lined up around it. So, each night the dots changed the position, proving they were moons orbiting Jupiter. And the bottom image is a modern telescope view confirming exactly what Galileo saw. So, this was the first time humans realized that not everything revolved around Earth. Next, Galileo saw Venus going through a complete set of phases, just like our moon. So, in the Ptolemaic system, Venus could only ever look like a crescent. So, this proved Venus orbits the Sun. Later, he also observed dark spots moving across the Sun's surface, proving the Sun rotates. Now, let's compare these two diagrams of Venus's phases. So, according to Ptolemaic prediction, that means in the Earth-centered model, Venus moved on a circle or epicycle, always staying between Earth and the Sun. Remember? That meant Venus could only ever appear as a crescent, never gibbous or full. Now, in contrast, Galileo's telescope showed Venus going through a complete cycle of phases: crescent, half, gibbous, and even full. So, what does this tell us about where Venus must be orbiting? The answer is Venus must orbit the Sun. So, this was one of Galileo's strongest piece of evidence for the Copernican system. And the Ptolemaic model simply couldn't explain these phases. So, now Galileo's telescope gave powerful evidence for the Copernican system, but instead of ending debate, it ignited controversy. So, let's see what happened when Galileo published his boldest book, the Dialogo. So, of course, Galileo's discoveries made him famous, but also made powerful enemies. His most famous book, the Dialogo, pushed him into direct conflict with the church. So, Dialogo compared two world systems: Ptolemy's earth-centered and Copernicus sun-centered. And Galileo chose to present his arguments as a debate between three characters: Salviati, who supported the Copernican model; Sagredo, who was neutral; and Simplicio, who defended the Ptolemaic system but was portrayed as not very bright. But the book offended Pope Urban VIII, who felt mocked, and the Inquisition accused Galileo not of heresy but of disobeying earlier orders. So, unfortunately, at the age of 70, he was threatened with torture, forced to recant, and lived under house arrest until his death. Now, this painting shows Galileo trying to convince scholars and church officials of what he saw. Some refused to even look through the telescope, saying, if the heavens were meant to be seen that way, God would have given us telescopes in our eyes. So, this shows how strong resistance can be when new evidence challenges long held beliefs. And the trial was not only about astronomy, it was about how we find truth. The church relied on faith and scripture, while Galileo argued that observation and evidence reveal nature. So, which do you think should decide scientific questions? Belief or evidence? So, although Galileo himself was silenced, his work, together with Kepler and others, sparked a scientific movement that could not be stopped. And over the next 99 years, astronomy was transformed forever. Now, let's look at the 99 years that completely transformed how humans understand the universe. From Copernicus' publication in 1543 to Galileo's death in 1642. Astronomy and science itself changed forever. Now, during this period, the Ptolemaic model with Earth at center gave way to the Copernican model, placing the Sun at the center. So, this was not just a small shift, it changed how people thought about the universe and our place in it. So, imagine how shocking that idea must have been at the time. Now, notice something important. The puzzle of planetary motion was not solved by debating philosophy or interpreting scriptures. It was solved using careful observation and precise calculation. So, this is really the birth of modern science. Now, at the start, no one had ever looked at the sky through a telescope. But by Galileo's time, telescopes and precise measuring tools had transformed astronomy into precise evidence based science. And these 99 years were not just about astronomy. Europe was in the middle of the Renaissance, a time when learning, travel, and culture were exploding. People were ready for new ideas, so when Copernicus published his model, the world was primed to accept the change. And Kepler showed how math could describe planetary motion, proving that mathematics is a powerful tool for understanding nature. And this was the beginning of modern science as we know it. So these 99 years didn't just change astronomy, they helped create modern science itself. And this sets the stage for everything we will study in later chapters about how humans continue to explore and understand the cosmos. And being said that, we have reached the end of the chapter. So let's move on to the chapter summary to review the key points. Now let's start at the very beginning. Long before telescopes or even written records, humans were watching the sky. And many ancient cultures tracked the sun, moon, and stars to guide agriculture, rituals, and navigation. And some left physical markers like Stonehenge aligned with celestial events. So these alignments show how seriously they studied the sky even without modern tools. Now, can you think of modern ways we mark celestial events today? Like solstices or eclipses? Next, in the second section, we learn about classical astronomy. So, in classical astronomy, thinkers like Plato and Aristotle imagined a geocentric universe, Earth fixed at the center with perfect celestial spheres rotating around it. But not everything fit this model. Planets sometimes move backward in the sky. Retrograde motion, remember, which was hard to explain at the time. So Ptolemy introduced epicycles, difference, and equals to make the math match observations. Even so, classical astronomers achieved remarkable feats. For example, Eratosthenes accurately measured Earth's diameter using shadow in sign. So that's impressive for over 2000 years ago. So then came the Copernicus in 1543. He proposed a heliocentric universe. Earth rotates and orbits the sun. So this was revolutionary because it challenged centuries of geocentric thinking. One immediate benefit, retrograde motion became easier to explain, and planets like Venus and Mercury could be treated like all the other planets. So this shift was part of a broader scientific revolution. The idea that simpler, more elegant explanations could replace traditional dogma. It wasn't just astronomy, it was a new way of thinking. Next, Tycho Brahe spent 20 years of making the most precise observations of the sun, moon, and planets before telescopes. So his data were incredibly accurate for the time. And Kepler used Tycho's observations to discover his famous laws. Planets move in ellipses, faster when closer to the sun, and the square of the orbital period is proportional to the cube of the semi-major axis. And the Rudolphian tables published in 1627 combined heliocentrism and elliptical orbits. So they could predict planetary positions up to 100 times more accurately than Ptolemy's system. Now in section 5, we learn about Galileo, who revolutionized astronomy by looking through a telescope. He saw phases of Venus, moons of Jupiter, and mountains on the moon, proof that the heavens were not perfect spheres. So this was evidence-based science in action. Rather than rely on philosophical ideas, he tested and observed directly. And of course, this led to a conflict. In 1633, Galileo was tried by church for supporting the Copernican model. It's a powerful example of how science and society can clash. And finally, let's zoom out. From Copernicus' death in 1543 to Galileo's in 1642. The foundation of modern astronomy and modern science were built. So science shifted to observation, testing, and mathematical analysis. And Kepler's work showed that math could describe nature with precision. And the legacy of this period is huge. Modern astronomy relies on observation, theory testing, and predictions. And this is the era that gave birth to science as we know it. And with that, we have reached the end of chapter 4. So take some time to review the key points we have just discussed. And make sure to go through the practice questions and complete your homework to reinforce your understanding.